before I introduce myself, I'm going to ask Adam Krolak, who's on the line from Poland, to introduce himself. Adam, if you would.
Good morning, good afternoon. This is Adam Krolak. I'm a marketing product manager for Honeywell level products. And although now I work with marketing, I have quite a practical background. I started as a service engineer, so I used to climb tanks and install level instruments, then calibrate and troubleshoot them, and also train customers on how to use them best, how to maintain them, and how to get the most out of level measurement. Then I transitioned to management role, and then I went to Honeywell R&D Center, and now I'm responsible for the level products of Honeywell. So thank you for joining this webinar, and I hope I will be able to answer your questions or add to this presentation. Thank you.
Thank you, Adam. So I'm Tom Brands. I'm originally from New Orleans, and I got a bachelor's degree in physics from Loyola. I worked, actually I joined Honeywell in 1996 and then went to work for Emerson for a few years and then rejoined Honeywell in 2014. I'm a technical solutions consultant, and my job really is to be technical sales support for pressure, temperature, level, and flow products. So I travel to the field. I support our channel partners like Relevant Solutions. I make customer visits, give presentations, and help with applications kind of questions. I'll be giving the presentation. Adam will be helping out with the Q&A sessions, and as you can see, we're going to go from general to more specific. We'll start off with the topic that there are many different ways to measure levels. So when somebody comes up and asks how we would measure level, it would the answer to that question would be another question, or questions to sort of qualify how the application to see what's the best way to do it. Sometimes the best way to measure level might be with a flow meter. We'll talk about radar, the basics, how it works. We'll talk about the advantages and disadvantages, because every technology that you come up with is going to have its strengths and weaknesses. We'll talk about non-contacting radar, the pulse type versus the continuous. We'll pause there in the middle of the presentation for a Q&A session, which Adam will lead. And then we'll pick it back up with contacting radar, the guided wave radar, how that works, and then we'll evaluate your application when you'd use guided wave radar. We'll wrap it up with a Q&A session and finally have a conclusion. So in this slide, we're looking at our world of applications. There are a lot of different applications for level measurement. On the left-hand side of the screen is inventory tank gauging. So this is where the customer may be using level for as a cash register. So for custody transfer that requires highly accurate level measurements. So one customer may be sending their product to a terminal location where it's stored, and then they're selling it to somebody else. And in that case, the level measurement is very important. And in this case, the accuracy requirements are very high. We're not going to be talking about that world of tank gauging. We'll consider that a separate application, probably for another webinar. Now, the general level measurement on the right side of the page, you can see we've broken that down into the solids, because some technologies will measure solids. And then when it comes to measuring solids, one of the things we're going to be concerned about are the pulling forces. Above the solids will be the liquids, and when it comes to liquids, we're going to have to ask questions about what density we have. Sometimes it's important to know what the dielectric constant is, and there may be an interface. Maybe there's more than one liquid in there, maybe oil sitting on top of water. Do we want to measure that interface? Additional questions would have to do with the vapor space. Is there foam on the surface? That may be a challenge for some level measurement technologies. Is there dust in the vapor space? That can create problems. Is the surface turbulent? And then you can see I have the sun over there in the corner. And when it comes to some technologies, the temperature effect, say for a DP with a capillary and remote seal, that might create some temperature sort of errors, that something we'd want to consider in selecting a level technology. So there are a lot of different ways to measure level. These are the ones we're going to cover: the differential pressure, ultrasonic, capacitance, floats, displacers, weigh cells, and then we'll look at radar, the non-contacting, and finally the contacting. Each has strengths and weaknesses. So when I talk about these, we'll talk about what it does well, and then what are the things that we need to be concerned about for each one of these. Differential pressure is simply a matter of measuring hydrostatic pressure. So if we measure pressure at the bottom of a tank and say compare that to atmosphere or compare that to the pressure at the top of the tank, as the level rises, the hydrostatic pressure increases. So the level is directly related to hydrostatic pressure. Some of the issues or concerns are that to do this, we're assuming a certain specific gravity. If that specific gravity changes, all bets are off. The level measurement will not be very accurate. The diaphragms or remote seals need to come into contact with the liquid. It could be a problem if there's corrosion. It works on liquids, but it doesn't work on solids. And sometimes capillary seals have an issue with vacuum, high or low temperature, varying process temperatures. And this is the case where the sun rising and setting at a location in a tank farm can cause problems with expansion and contraction of the fill fluid in those capillaries. Now, on the strength side, if there's foam on the surface, if there's a turbulent surface, differential pressure it's not going to be a problem with differential pressure. Ultrasonic transmitters. These work by sending a sound pulse. So if you remember from your science classes, a sound wave needs air to propagate or some sort of medium to propagate. It won't propagate in a vacuum. So we know that the speed of sound is 1,100 feet per second in air, and that's at a certain pressure and temperature. So we're assuming the speed of sound, and then what we do is send a pulse down, and that reflects off the surface and comes back up. So we see how long it takes for the pulse to go there and come back. We know the speed of sound, and then we know the distance. So the accuracy is based on the speed of sound. That speed of sound, that 1,100 feet per second, can change if the vapor pressure, if the temperature has changed in that space. The pressure that we just said, pressure and temperature make up that vapor space, and foam and dust can reduce or eliminate the echo entirely if that's in the vapor space. Now, if you have a basin with water, it's a vented situation, these work very well. Capacitance. Capacitor's a device that measures the capacitance between two plates, and there would be a dielectric material between the two plates. So the distance of the plate and how much dielectric material is between the plates, that gives us the capacitance. So in our case, when we're using a capacitance level gauge, the rod is one plate, the tank wall is the other, and the material in the tank rises and falls, and that changes how much dielectric material is between the plates. That's how we get capacitance. The readings are very much affected by the electrical characteristics of the product. Specifically, we're assuming a certain dielectric constant of that material that's between the rod and the tank wall, or in other words, between the two plates of the capacitors. If that dielectric material changes, the accuracy is going to be affected. Sometimes calibration can be difficult. You have to get the zero reading, you have to empty the tank out, and then to get the full scale reading, you need to fill it up to full scale and do a calibration there. Finally, the rod comes into contact with the liquid. So this could be an issue if you have a corrosive liquid. Float type transmitter, this one that we're showing has a magnet in that float, and it really just works off of a buoyant force, so that as the liquid rises and falls, so does that float. That float is a magnet, and in the rod are a series of reed switches. So as the magnet in the float passes over the reed switches, it opens or closes them. And these reed switches, when they're closed, form a series, and you can measure the resistance there and get the level. So you have to, when you're selecting a float type, you need to consider the specific gravity. And whenever you have something like a moving float, you have to be concerned with sticky fluids. Maybe if there's a slurry or something in it that may jam the float. It doesn't work on solids, and again, it comes into contact with the liquid that we're measuring. A displacer is typically mounted in a bypass. We'll take a look at a bypass later on in the presentation. So you can see the bypass here on the left side that would be mounted off the side of a tank. And in the bypass would be a float, and this works off the principle of buoyant force. So if you had the float just hanging in there with no liquid in the bypass, it's a certain weight of the float, and that's what we're measuring at the top, is the weight of those floats. As liquid comes into the bypass, it creates a buoyant force, and that reduces the weight that we sense in the displacer transmitter. So as the level rises in the bypass, that weight that we measure decreases because of buoyant force, and that's how a displacer transmitter works. Displacer assumes a specific gravity of the liquid. Just like our DP, if that specific gravity changes from what you assumed, level is going to be affected. It doesn't work on solids. It comes into contact with the liquid that we have to measure. Some people say there are concerns with just the mechanical nature of this, wear and tear over the years and maintenance, and other people don't seem to have so much of a problem with it. So it's inconclusive. that question is inconclusive. Weigh cells. So weigh cells be mounted underneath the tank. Of course, the best way to install those is during construction, initial construction, and they're just measuring the weight of the vessel, or particularly the material within it, and that weight can be converted to level. These assume the specific gravity, so we measure the weight, we know the specific gravity, we can get the level. If the specific gravity changes, that assumption is not correct. Weigh cells are difficult to put in after the fact, and they can be expensive. Weigh cells are also very sensitive to installation, so they need to be put in correctly for them to work right. Okay, so we said there's a lot of different ways to measure level. They have their strengths and weaknesses. We'll get to radar now. Two main types in general here would be the non-contacting and then the contacting, or guided wave. The non-contacting could be the frequency modulated continuous wave or the pulse, and we'll talk about the differences between those two. And then the guided wave radar, we'll spend really the second half of the presentation on that. So the pulse type, the radar, this is non-contacting. The illustration is showing the continuous wave there on the left, and then the pulse on the right. So the continuous wave is sending out a wave that changes frequencies, but it's continuous. The pulse type is just sending out a pulse and seeing how long it takes to go off the surface and come back. So in this case, we're emitting a microwave pulse. It's electromagnetic radiation, so it doesn't have to have a medium to propagate. So it can propagate in a vacuum. So it's traveling at about the speed of light. So we send the pulse out from the antenna, and we measure the time it takes to go down to the surface, bounce back up, and come back up to the antenna. We count that time. We know it's traveling at the speed of light, and from that we can get the distance. Now the frequency modulated continuous wave, again, a continuous wave going out, it's changing frequencies at a precise rate. And if you can see from the graph at the bottom, as it's changing frequencies, if you look at the frequencies at any given time, or look at what's being received at any given time, you can look at the difference in frequency, and that is converted into the level of the tank. Okay, so continuous wave, changing or modulating frequencies, we're looking at the difference in frequencies, and that gives us tank level. Okay. So we've gone through the different ways of measuring level. We've looked at the pros and cons of each one. We've looked at radar somewhat, and we'll pause here for a Q&A. And I'll turn that over to Adam.
I don't see any questions in the chat box. Alicia, can you see questions there, or?
I'm here. It doesn't look like we've had any so far.
So maybe there is some time needed to enter them. So let me answer a question that we frequently get, which is which non-contact radar frequency option should be chosen. When we look at the market, there are two common frequencies. One is lower, this is about 6 gigahertz, and then there is another frequency that is close to 26 gigahertz, and of course it depends on the vendor. So there is a concern which one should be chosen for a specific application. So when we look at it, the higher frequency, the 26 or close gigahertz, is suitable for most applications. It comes with less installation considerations. The beam angle is narrower, which makes it easier to install in narrow or busy tanks. And the energy from the antenna is more focused. So the measuring range is usually longer. On the other hand, the low frequency models, they provide better performance in difficult applications. And by difficult applications, I mean applications with foam or with disturbances. The low frequency beam can easier penetrate foam or vapor in the tank, so it's more robust in this case. Also, the wider beam that is generated with 6 gigahertz signal sometimes can average the surface that it looks at, and when there is an obstacle or maybe a mixer right below the instrument, it's quite possible that it will be possible to take it out by processing of the signal. So to this question, I would say that 26 gigahertz is more common for typical applications, and 6 or close to 10 gigahertz would be for difficult applications with foam, with vapor, or with moving parts inside the tank. Okay, we don't have any other questions yet, so let me look at some other questions that we commonly get. For non-contact radar, it's a question: what type of antenna should I use? Because we have these horn or cone antennas. Then we have rod antennas. Some vendors have parabolic antennas, and then there are special types of antennas like small horn with PTFE or other coating. It's called process seal, for example. So the cone or horn antenna is the main commonly used antenna. It's the only antenna that should be used in bypass or stillwell applications. And also in a free space, it gives a thinner or more narrow beam with angles of 8, 9, 15, up to 20 degrees. And when we compare this with rod antenna gives us angle of about 40 degrees. so it's much wider, and rod antenna should be normally used only for applications or installations where the process connection is too narrow or too small to fit a horn antenna. So that's the general guidance.
We have a question. It says, does the radar require an external power supply, or can it use the power from the analog side?
There are both kinds. The more popular now are loop-powered radar instruments, so they are powered through the 4 to 20 milliamp loop, and there are only two wires needed to both transmit the signal to and from the radar and to power the radar. But there are also radars that are four-wired, where the power is separate to the communication signal.
Okay.
Yes, I think we can continue, and then hopefully you will have more questions at the end.
Okay. Thank you, Adam. We'll move on. We'll get more specific with guided wave radar. And guided wave radar works off of the principle of time domain reflectometry. This has been around for a while. Telephone companies have used this for a long time. So imagine a telephone company with a network of buried wires throughout a metropolitan area, and if there's a line break, they want to know where that line break is, where to send a technician for the repair. So by using TDR, what they'll do is hook up a device to the end of a wire, send a microwave pulse down the wire, and see how long it takes to go there and reflect off of the break and come back to the original source. So we'll see a reflection at that break. We know it's traveling at the speed of light, and based on the time it takes to go there and come back, we know approximately where the break is and where the technicians need to dig to go in and make the repair. So in this case, we're sending the microwave pulse down a probe inside of a tank, and that probe is essentially a waveguide. We know it's traveling, the pulse is traveling at the speed of light, so we measure that time, and we can get the distance. Okay. Wave properties, this is going to be in the microwave range, and really where we see the reflection is where there's a change in dielectric. So if you have a tank with water with air on the top, the dielectric of water is 80, the dielectric of air is about 1, and you'll see a nice strong reflection where there's a difference in dielectric. So here's another look at it, is as the microwave pulse is sent down the cable where it sees that difference in dielectric, there will be a reflection, but not all of the energy is going to be reflected back up to the surface. And that's what we're trying to show here, is that where you have that change, part of the signal is going to be reflected back up to the surface, but part of it is continues down the cable past the interface. And we're going to see that that's important and actually lends itself to a nice feature for interface detection. I'll set this one up, the interface measurement, with an illustration from the oil field, from upstream. When oil companies are producing from a well, what comes out of the ground is a mixture of oil and water and gas. What they'll do at the surface is separate those three things, and they'll send the gas off to a pipeline. They'll separate the oil and water, and they'll put the oil into an oil production tank, and then they'll put the water into the water tank. So the operator is concerned about the level in those tanks, particularly about the oil tank, and he wants to know when the level gets high enough he wants to know when to send the truck out there to pump out the tank and send it off to the refinery. He also wants to make sure that the tank is not overfilled. He doesn't want to have a spill and cause an environmental issue. Now, the separation that occurs there at the well site is not perfect. So in his production tank where the oil is, there will actually be some water that settles out at the bottom. So he wants to measure the surface level so he knows when to send the truck out. He wants to make sure he doesn't overfill. But he's also got an interface down there between oil and water, and he wants to be able to track that. So with guided wave radar, we'll get the reflection off the surface. We'll also get a reflection off of that interface, so the operator will know when to go out there and he can drain off the water at the bottom of the tank and make more room for oil. So guided wave works real well for measuring the surface level and the interface. Now, when you're making an interface measurement, there are some questions about the difference in dielectric between the upper and the lower products, and also the thickness of the upper product as well. So when would you use guided wave radar? It would be best applied when there's unstable process conditions where you have changes in viscosity, changes in density. We saw that changes in density causes problems with DP. Might be agitated surfaces with dust or foam, and we saw that sometimes foam can cause problems with non-contacting radar and say with ultrasonic. High temperature and pressures. Performs well in high temperatures, and that would be, say, compared to ultrasonic. It works in solids, and none of the technologies we talked about so far, except for the way cells, would work with solids. So this might work with grain, catalyst, polypropylene pellets, and then the interface detection. Guided wave radar does this very well. And finally, we talked about how these are powered. Some of the devices are 4-wire powered, and that would maybe say that for inventory tank gauging, I guess, would be the most common. But for the general applications, most of these are 2-wire devices. They're loop powered. So advantages, disadvantages. We really talked about the advantages so far. The long range would be, say, up to 150 feet. And they're mounted at the top and don't have low sensitivity to foam and buildup. And we talked about interface measurement. Now the disadvantages are, of course, that it comes into contact with the process, and if there's issues of corrosion, maybe an issue. If there are strong currents in the tank, maybe if there's an impeller or an agitator, you want to make sure to avoid contact with that. If it's a solids application, we want to be careful about pulling forces, or if it's a very viscous type of material, the pulling forces on the probe could break off the probe. And finally, buildup. Buildup that may occur on the probe if the dielectric's high enough, that would cause a false reflection. So different ways to install these. The application, if we look at A, is kind of a typical application where we're mounting it at the top. It might be mounted right there to the roof of the tank, or there might be a nozzle or riser that comes off the roof of the tank. And B and C are kind of special installations. So if you look at B, in this case we're mounted at an angle. And what's important to remember is that we're measuring the time or the distance that microwave pulse is traveling along the probe or rod itself. So that distance is not really the vertical distance that the operator is interested in. So if we know that mounting angle with just a little bit of trigonometry, we can convert that angled distance into the vertical distance, and that's what the end user is looking for anyway. In case C, if there's an instance where you don't have a lot of room overhead, you might want to mount it from the side. I think these are pretty unusual. Okay. And then the illustration I'm showing in the top right, it's just sort of reinforcing that we're sending out this this microwave pulse that reflects off the surface, and what we're measuring directly is that distance. We're actually measuring the time and converting that into distance, and that's the distance from the flange down to the surface. So most people are interested in level as opposed to difference. And if we know the tank height, or the height of that flange, we say tank height minus distance gives us level. So some things to be concerned about is tank walls, non-continuous tank walls. Our recommendation is to mount the Honeywell guided wave radar at least 6 inches from any obstacle. And you need to be concerned about tank walls. If the tank wall is smooth, it really wouldn't be an issue. In fact, the space between the tank wall and the probe would actually help to focus the energy. But if there are seams or some sort of inconsistencies on the tank wall, those could cause false echoes. So there might be things like ladders and coils and impellers we want to be careful about and not to interfere with those. There might be things like point switches or probes that are in there that would give us reflections, and we want to be able to discriminate those from the surface level. And finally, jets of medium, we wouldn't want to mount those in an inlet stream. So recommended mounting positions, you can see the happy face over there on the left where we're avoiding obstacles, staying at least 6 inches away from, say, a tank wall or some sort of obstacle within the tank. And you can actually mount in the middle of the tank. We have sort of the cautionary indication there. But if the reason you'd want to avoid mounting a guided wave radar in the middle of the tank is if the roof is flexible. That flexing of the roof would actually change our tank height or the reference height that we're using to get level. So that could cause a problem if your roof is changing its height right there in the middle. For non-contacting radar, I think it's more important to avoid mounting in the middle of the tank, particularly if it's a domed roof, because that could act as a parabolic antenna. And definitely want to avoid mounting guided wave radar in an inlet stream, as we're showing there on the right. A couple different installation types with different probe types. So this could be mounted, as we're showing here, and just mounted right onto the roof. We're not having any issues with a calm surface. We're not having any issues with turbulence on the surface. Now, if there were issues with turbulence, we could mount these in a stilling well. So often the operator or end user would have a stilling well. So it's just a cylinder, a perforated cylinder installed in a tank, and its purpose would be to still or calm the surface. And then here's the bypass we were talking about earlier with our displacer type transmitter. So that's a bypass, and the level in the bypass is changing with the level in the tank. This also helps to calm the surface, and this is typically how a displacer is mounted, but these guided wave radars can be mounted in that same bypass that a displacer is in. Okay. As you can see, the measurement range in a bypass is limited to where the inlet and outlet are in the bypass. Now here's a look at an installation. This was an installation I visited in Vancouver, and fortunately it was in the winter time, so it was not too bad of an experience. But this is in a tallow oil tank, and below I'm showing the echo curve, and what you see on the left is the reflection right there as the microwave pulse is leaving the transmitter, and that's showing the reflection at the flange. And then further towards the middle of the graph, you can see the reflection off of the surface. So we're able to detect that surface, and that gives us the distance. We change that distance into level. And you can see from the picture, it's a little bit dark, but in this case, it's a threaded connection. It's going right into a manhole cover on top of this tank. So one of the things you'll want to select here is the probe type. There's the rod, then there's the rope and the coax, and the rod will go up to about 18 feet. And it used to be that we thought the rod or probe had to be a continuous, manufactured as a continuous rod. So imagine you had an 18-foot application, it would have to be a continuous rod. And we found that these can actually be manufactured in segments and installed in segments. Much easier to manufacture, easier to install. So imagine trying to install an 18-foot probe in a tank. But these can be manufactured and installed in segments, and there's no degradation in performance. The rope type can go up to about 150 feet, and you would typically want to have a weight on the end of that to hold it taut. And if you can see it there, there's some set screws so that that weight can be moved up and down on the rope, and these can be cut to length. There's nothing magic about the probe length other than that is your measurement range. And finally is the coax. This looks a lot like the stilling well I talked about before. So if the customer installs it, we call it a stilling well. In our case, we're providing this perforated cylinder around a rod, and we're calling it a coax, and that's how the probe would be ordered. This comes in segments as well, and the purpose of the coax is similar to the stilling well in that it serves to still the surface, and it also focuses the energy between the rigid probe and that coax or perforated cylinder on the outside. So probe selection's important. So for most applications, we're looking at the wire type probe, and the coax, it makes sense you'd want to use that with clean liquids. If you have a low dielectric constant, that might be the best way to go because it's focusing the energy. So I said before, you get the reflection where there's a difference in dielectric constant. So with a big difference, say between air and water, you get a nice strong reflection. If the difference is not that great, you get a weaker reflection. So where you have a lower dielectric constant, you're getting a weaker reflection. It might work better to have a coax where you have that focused energy. Now, getting down to the next category, viscous liquids, the choice would be the single wire or the single rod. And when it comes to viscous liquids, that's where we'd want to be careful with the coax probe. Okay, and then the single rod can be used with the angled installations, and so the coax is going to help to focus the energy, and it's going to help us to avoid obstacles where you might have some interference for false echoes. Okay. So specifying level instrumentation, if somebody came to us with a level application, it might be one of our customers, it might be one of our channel partners, they would say, well, okay, I've got a level application, and the response from Honeywell will be, okay, here's a 2-page application data sheet. You need to fill it out completely before we are going to do anything else. We want to understand the application. And from everything we've said so far, I think you realize how important it is to understand the application before you specify anything. So they would fill out the application data sheet. We'd send that off for review, and it might take a couple days for somebody to review the application data sheet and determine whether this is going to work or not. So most people really don't like filling out these data sheets. It takes a little while to get response, and we think there's a better way to do it. And what I want to do is introduce a tool that we have that will make it much easier to go through this process to qualify the application. So really to reinforce this idea of how important it is to understand the application, I did a ISA webinar with Hunter Vegas, and he works for an engineering outfit, and during his part of the presentation he was talking about the importance of specifying level instrumentation, understanding the application. He says radar using these technologies can be very vendor specific. It's different, a lot of different technologies, a lot of components, a lot of choices. He really recommends getting your vendor involved, and that's what we want to do, is to be consultants or advisors to talk about what are all the different pros and cons when it comes to selecting the best way to measure levels. So this is a customer, one of our, that really recommends getting some help from the vendor to detailed tank geometry and information and so forth to make sure that we're matching the right technology to the application. So with that endorsement from Hunter, I'll go on to say this is what we came up with. So instead of using the application data sheet anymore, we've developed a cloud-based tool, and that's what you can see sort of in the upper right-hand corner. And customers, channel partners, anybody can get to this through the internet, and what you're going to do is use this to qualify the application to see whether this is going to work or not, and also to develop a part number. Okay, so the rest of this page is really just showing the process once we've qualified the application and built a part number, how that would go on for manufacturing. But the important point to note is that this is cloud-based, and that this is where you can go on to easily qualify the application and build a part number. And it's accessed here at this website. There's no username or password required. Anybody can get access to it. And it's supported by these browsers, Internet Explorer 10 and newer. And then it works on mobile devices as well. Okay. So what does it do? This is the opening page, and it's going to come up and say, we suggest you have the following information available. So you've got a list of all the things, the information that you're going to need. So you don't have to go chase it down as you're stepping through this, running back and forth. It validates the specific application. Is guided wave radar going to work here? And then finally, it's going to do a configuration. It's going to build a model number that can be used to go on for a quote. So here's our validation process. So we go on to this application validation toolkit. We go on to this website. It's going to have a guided setup. So it's going to step us through these different tabs that you can see in number 1, the tank shape, the tank measurements, the obstacles, and so forth. Of course, you'd select what units you wanted to use. And it gives you a graphic representation. So as you're building this up, if you select a vertical cylindrical tank with a domed roof, you can see it being illustrated on the right as well. And if you have an obstacle, you can define that obstacle as far as its diameter, its height, where it is in the tank, and so forth. And number 5, the Inline Help, if one of the questions comes up and you're unsure about it, you can mouse over that blue dot, and that's going to give you additional information about what it is we're looking for in that section. So the built-in logic and warnings on number 6, this is pretty important. So if let's say you fill out the application data sheet, and in the the old way of doing things, you put in that the temperature is 450 degrees Fahrenheit, and you put that in the beginning, and without knowing that the limit of this, the Honeywell guided wave radar is 400 Fahrenheit, without knowing that, you fill out the whole sheet, it goes off for review, and 2 or 3 days later you get a reply that says, no, this is not going to work, the temperature's too high. So all that work really for nothing, and it's been a delay of a couple of days. The application validation toolkit gives you a real-time response. So as you're filling this out, if you put in a temperature over 400 degrees, it comes back with the indication that it's not going to work. Our temperature limit is 400 Fahrenheit. You can't exceed that. So this is not a good application for guided wave radar. On the other hand, that's pretty much of a hard rule. It also has warnings to say that, for example, if the nozzle length is beyond a certain number, then we'll give you a warning, but we'll go on to say that indeed you can use that, but be aware that we just warn that that may not be the best way to do it. So certain warnings will allow you to go on, certain hard stops will not. And as you're building this out, it's giving you visual indication to include visual warnings. So in number 7, I've specified a rod length that is too long because it interferes with an impeller. So you can see the impeller at the bottom of that tank. The rod length interferes with that. I've gotten a visual warning for the interference. And as you're stepping through this, as you can see on number 8, we're building a part number as we go. And each application that you do will have its own unique URL, and you'll get an email. So the initial page will ask for your email address. You'll get an email back, and that will have your URL. And what I do is save it to my favorites. I give it a name that's unique to the application. So I know what that URL is linked to. So you've got that email, it's got your URL, and you can come back at any time. So as you're going through this, you may get interrupted, have to stop and continue later. That's not a problem. Or if you're going through this or you've completed it, you may want to replicate this particular tank, or you might want to send this off for somebody else to review. And finally, this allows for online collaboration. If you're going through the application validation toolkit and you get stuck and want somebody else to take a look at it, we can get on at the same time. We can look at the same application and step through it together. Now this was the opening page, and so it's asking for your email address, and it asks for a short description of your installation. So you'll get that email, and in the subject line it will have this description. So this email would say John's Tank 123 in the subject line, so you'll know which one this is referring to. You know where that URL is. So once you've completed that, you get a clear sense of completion. You get a list of all the parameters and selections that you've made, sort of a summary that you can print out, as well as a drawing of the application. So we validated the application, and now we've created a model number. It's kind of hard to see in this page, but sort of the middle of the page to the left, it's created a model number for this particular application, and it's added unique 5 characters to the very end of the model number that ties this model number, this selection, back to the work that you did here in AVT. And in that way, we can pre-configure the radar for your particular application, so we have the best chance of this working out of the box when it lands on the end user site. So we've covered a lot of ground. We talked about our world of applications, all the different things we need to be concerned about, whether it's inventory tank gauging or just general process applications, the measurement of solids versus liquids, and when it comes to solids, we were concerned about the pulling forces, and with liquids, we had to know what the density is, the dielectric constant. There might be an interface. In the vapor space, we were concerned about foam and dust, and there might be turbulence as well. We learned that there are a lot of different ways to measure level. Each has their own strengths and weaknesses. We covered a lot of different technologies. And we talked about radar, the non-contacting versus guided wave. Talked about the pulsed versus continuous wave. And then we spent most of the second half here focused on the guided wave radar, how it works, and then when it is that you'd use it. And finally, the application validation toolkit is a way to validate that application and build a part number at the same time. So we're ready for our second Q&A section here.
So I definitely have 3 for you. The first one says, how much of an interface is required to detect an interface?
Yes, that's a very good question, because what the instrument is looking at, it's looking at a difference in the electric constant. And when we measure interface, the typical situation would be when we have oil or some hydrocarbon on top and a high dielectric constant liquid in the bottom, something that is water-based. So on top of this high dielectric constant, we want to detect low dielectric constant liquid, which is the hydrocarbon. And usually there is a minimum thickness layer that the vendors would give for the given instrument to detect the upper layer on the high dielectric constant liquid. So currently for the Honeywell guided wave radar, the upper minimum layer is 380 millimeters, and we are working to decrease it to 130 millimeters. So this is the value for the next release in a few months.
The next question is, how much of a dielectric difference is required?
Yeah, so as I said, the instrument requires a difference in the electric constants to see a border, to see a reflection from the change in those different liquids. Currently, the minimum difference is 10, so the dielectric constants should differ by at least 10. And also there is a restriction on the upper and lower liquid. So the upper medium, upper liquid should have a dielectric constant of less than 8, and the bottom liquid should have a dielectric constant of minimum of 18. So as I said, usually the upper liquid is hydrocarbon with dielectric constant close to 2, and when the bottom liquid is water-based, the dielectric constant would be close to 60. So those restrictions are met very well. Thank you.
So I have a few more questions. Is there a rule of thumb about the clearance needed around the probe? How are the nozzles addressed?
Yeah, so rule of thumb would be about 6 inches of clearance around the probe. The nozzles are, there is a table with recommended nozzle height and diameter in the manual of most vendors. Nozzle up to 300 millimeters is usually not a problem, and nozzle with ID of 2-inch or larger. But usually measurement is possible even with taller or larger nozzles. Sometimes some part of accuracy may be the accuracy may be lower, but this is vendor and application dependent.
The next question says, how many levels can we check for at one time with guided wave radar?
We can measure 2 levels. One is the interface level, and the other one is the, let's say, top level. So we can measure the total level in the tank and the level of the interface. That said, some guided wave radar instruments have 2 outputs, 2 analog outputs. So then one of the level can be sent through one output and the other can be sent through the other output on the analog output. If the instrument is equipped with hard communication, then both levels and other variables can be read at the same time. If the instrument has only one analog output, then the user needs to choose whether he wants to send out the interface level or the total level in the tank.
Alyssa, are there any more questions?
There are quite a few more. So the next question is, can you use a guided radar on an open tank? And if so, do you sell a mount for this?
Yes, of course, the radar can be used on open tank. There is no issue with it. If the radar has a flange connection, then it can be used as is. If the radar has a threaded connection, a small reflecting metal plate is needed at the process connection to reflect the signal and concentrate it around the wire. As far as additional mounting on top of the tank, Honeywell doesn't offer these. As far as I know, other vendors don't provide custom-made mountings. The instrument comes with a process connection, which is a flange or a threaded connection, and it can be mounted into a frame or a holder provided by the end user. Thank you.
The next question says, how well does the non-contact radar handle buildup? We are a mining plant and deal with a lot of dust and particles in the air.
In general, it handles build-up quite well. I understand that the dust or the particles would stick to the antenna, let's say a horn antenna. So I would recommend an antenna that is sealed with plastic so that the particles don't go inside the antenna. There are antenna versions with purge options where the horn can be purged with pressurized air. This often helps with anything sticking or coating the antenna. For dust, the lower frequency of 6 GHz may be better. This application is definitely doable, but would have to be considered with all the details, like tank mounting, the range in the tank, the dielectric constant of the medium. Yeah, so we can please contact me on an email and I will review this application with all details. Thank you.
So the next question says, is there any issues with ice buildup causing signal problems on the guided wave radar? I'm asking this question because I'm in North Dakota and we have a lot of extreme cold.
Yes, if there is an ice building up on the probe and ice has quite a large dielectric constant, so it can give a false reflection. Another problem might be a weight of the ice. If there would be a lot of build-up, it could be a problem sometimes for the probe, but often also for the roof of the tank. So I would have to look at the specific application. But frozen water can be an issue if it's in the measurement range. There is a number of techniques to suppress or avoid false echoes, and they are offered by almost all vendors. An interesting solution that is used in the Honeywell guided wave radar is a correlation algorithm. This algorithm has an internal example or internal sample of reflection that the instrument is looking for, and then the instrument is trying to match this sample shape to the shape of the reflection that it gets from the tank. This way, this algorithm is quite robust to false echoes or false reflections, because it only takes into consideration reflections that have certain shape that is predetermined in the instrument. Thank you.
The next question says, with GWR or even non-contact radar on solids, how do we deal with peaking or sloping of product in vessel?
Yes, so for non-contact radar, we may have some more averaging, although the slope of the material in the tank often influences the strength of the reflection. For guided wave radar, we measure only in a very small area around the wire that goes through the surface of the material in the tank. And depending on the angle of the repose, it is possible to predict the amount of the material in the tank, although we have to consider that we measure only in one point. So the real level, or for sure the volume of the material in the tank, is often different than the measurement. Sometimes measurement in 2 or 3 points is considered for greater reliability.
The next question says, can we see the signal levels on a chart, or do we need special software?
Oh, I wonder if that's referring to the echo curve that I showed for the tallow oil. So we talked about the application validation toolkit, and that's the software that we run, or cloud-based application that we run before the the unit's installed. After the unit's installed, if you want to go in and change parameters or look at that echo curve, we use a software called Pactware. It's not proprietary, it's consortium-based, but we use Pactware with a DTM to go in and make changes after the fact, and also look at the echo curve.
Mm-hmm. Also, if the question is about the measurement itself, the advanced display in Honeywell guided wave radar provides a trend option. So the consecutive measurements can be trended and visualized on the display. The digital communication or the analog output only sends the current values. So to trend the measurement in the tank, an additional system with visualization would be needed, which we can also provide, of course.
Right. And one last comment is that echo curve that I showed is just a snapshot. It's not a continuous display. It's a snapshot at a given time.
I believe that's all the questions. I just want to let everyone know that this webinar will be available on our YouTube channel for you to review, watch again, kind of see if there's anything that you may have missed during the presentation. We also have a couple of gas detection as well as gas and fire detection webinars on our YouTube channel as well, and we will continue to record these webinars and place them on that channel. So Adam, Thomas, anything else?
Thank you very much for your attentions and all the questions. They were very interesting, and hopefully we answered them to your point.
Yes, thank you, and you have our email addresses there.
All right, well, thank you guys so much for presenting this presentation, and the audience, thank you guys for coming. In the month of March, it will be valves. We'll have AT controls as well as Northeast coming in and making a webinar on basics of valves. So tune in. Thank you guys again, and enjoy the rest of your day.
Thank you. Have a great day.